Welcome back, part 2 of moles. This time I'm going to try and get into calculations. Well, I'm not going to try, I'm going to get into calculations. And whatever you might think and whatever you've been taught by your teachers in whatever schools you're at, the only way to do moles is my way. I know your teachers will say their way is better, but sadly they're wrong. I used to think I had my own way of teaching moles that was better. But then, after about 10, 15 years of teaching, I realised that there is only one way. And it wasn't my way that I started teaching with. It was the way I'm going to develop now. So, I don't care. Over the years, I know you might think I'm a fuddy-duddy, but I'm not. There is only one real way to get to grips with moles successfully over and over again. And I'm going to teach it to you in this video, which I hope will be about half an hour. So, last video, we got to this point. The first mathematical equation I wanted you to learn. That equation allows you to deal with real chemicals, and it allows you to deal with measuring masses on a weighing machine, on a balance, measuring masses of real chemicals. You can convert that to number of moles. This equation here that I've got in green, you learn it, learn to rearrange it. You've got 3 unknowns. Sometimes you'll be given 2 of them. You've got to work out the other one. You may be given the MR value, a number of moles, and worked out how much mass you've got. Or you might be given the mass and the number of moles and work out the MR value. Any one of those 3, rearranging them is a mathematical exercise, and you should be able to do it. And some people use those daft little triangles that have 3 unknowns, and then it allows you to work out the... Look, whichever way you do it, it's a mathematical thing. I don't really want to get into the maths of it, but you can actually use the maths. I prefer rearranging this equation. If you like those triangles, then as long as you use them correctly, get the right answers, I don't really care. But rearranging the equations is really what I want mathematically for you to be able to do. And we're going to be needing that skill later in this video. Right. Now, I said to you last video that there are 2 other equations you need. You need to be able to deal with volumes of gases, and you need to be able to deal with solutions. So let's get on to gases and volumes. So with gases, we can measure the weights. You can get a gas and you put it on a balance, you measure the weight of it. Some gases are really quite heavy. It's like you pick a balloon up of the gas and it's kind of feels as though you've got substantial material in there. And you stick it on a balance, it'll register as a weight, etc. And we do talk about weights. However, with gases, it makes sense to talk about volumes. So we can deal with weights like previous slide. This slide can deal with volumes. With gases, we can measure their volumes. Now, it is a very strange thing. Certainly when I first came across it, I used to think it's strange. It's common sense now. But it's a strange fact that every gas at room temperature and pressure occupies a volume of 24 litres. What? Any gas occupies a volume of 24 litres if you got a mole of it. What? Surely the gases have got different sized molecules. If you've got big molecules, surely that gas should occupy more volume. Well, no. That's what I used to think when I was your age. But you realise that how much gap is there between gas particles? And the gaps are really quite big. Typically, if you got a gas particle that size, the nearest neighbour will be 1,000 times that size away. And what's between the particles? Between the particles is nothingness. Between the particles is space or a vacuum. So, what if you make the particles bigger? If you make the particle bigger, they just take up more of that space. Making particles bigger does not affect the overall volume of the gas that we have. So volume is not dependent on size of the gas particles. It just depends on how many particles that you've got. So a mole of hydrogen gas weighs 2 grams, got a volume of 24 litres. A mole of carbon dioxide gas weighs 44 grams, but it's still got a volume. What we're trying to say is the volumes of gases, 1 mole, all every time they weigh different amounts, but they will all of them have a volume that's the same, 24 litres, at room temperature and pressure. Now, I explain it like this. So I've tried to draw small little dots for hydrogen, because hydrogen is pretty small molecules. Carbon dioxide is pretty big molecules. I put dots here. I put small circles there. And a mole, with that big number, 6 and 23 zeros, a mole of those in a balloon, 24 litres. A mole of hydrogen in a balloon, 24 litres. The bigger carbon dioxide molecules simply take up more of the nothingness, more of the space, more of the vacuum that exists between the particles. So the size of the particles just takes up nothingness that exists between particles and therefore doesn't affect the volume overall. Now, you just need to accept a mole of any gas at room temperature and pressure will have a volume of 24 litres. And that leads us to our second mathematical equation that we must learn. There it is. Number of moles of gas. Number of moles of gas. Number of moles of gas. This is gases and volumes. Number of moles of gas is whatever volume, measure it in litres, divide by 24. So volume in litres divided by 24, that is, learn the second really important equation, mathematical equation, which we're going to use for our calculations. And this equation, of course, can only be used with pure gases. So we can deal with masses of anything. We can deal with volumes of gases. And there's one more equation, which is solutions, before I then tell you how to do calculations. Students get confused by this, and so I'll put in a slide to talk to you about conversion of centimetres cubed to litres, etc. And people do not understand this term, decimetre cubed, and you need to understand that because that's what the exam boards use. Instead of the word litre, they call it a decimetre cubed. They use dm cubed. Now, point 1, you should already know that in a litre you've got 1,000 centimetres cubed. 1,000 centimetres cubed is a litre. So to convert centimetres cubed into litres, you need to divide by 1,000. To do it the other way around, if you've got litres, you want centimetres cubed, you multiply by 1,000. You should know those 2 points already. They're common points. What's not so well known at this stage is this cube. 1 decimetre, 1 dm, 1 decimetre, 1 dm, there, dm, is 10 centimetres long. So 1 dm being 10 centimetres long, decimetre is a tenth of a metre, 10 centimetres long. A cube is 10 by 10 by 10 centimetres, is a 1 decimetre by 1 decimetre by 1 decimetre cubed. So the cube, this cube, is 1 decimetre, 1 decimetre, 1, is 1 decimetre cubed in volume. 1 decimetre cubed in volume is 10 times 10 times 10, 1,000 centimetres cubed. 1,000 centimetres cubed is 1 litre. And there we have it. Litres is the same as writing decimetre cubed in exams. Do not let them confuse you. Moles per litre is written mol dm to the minus 3. I want you to know dm cubed is the word litre, and dm to the minus 3 is the word per litre. So when you see minus 3 is per litre, when you see dm3 is litre, mol is an abbreviation for mole, moles per litre, mol dm to the minus 3. And that's what they're going to use for solutions. And you may be, the top 2 points, you may need those to convert centimetres cubed of a gas volume into litres if we're dealing with volumes of gases. So a little bit of mathematics, terminology. You definitely need to know what a litre is, and you definitely need to know what the abbreviation for a litre in exams, dm cubed, or dm to the minus 3 is per litre, etc. Okay, so I find increasingly as I teach year in, year out, people know less and less about conversion factors, mathematics, the concept of a decumeter, etc. And I find that this, which I never used to show this slide 20 years ago, everyone would know this, and now I have to show the slide, otherwise people are confused. So please get your mind around the slide. I want it to be part of your general knowledge. You're going to need it to do the calculations. So let's get into solutions now, to develop the third equation with you. Let's be clear what we're talking about. Solutions. And again, we're talking about pure solutions. Pure solutions are you get something, a solvent, and you dissolve a solute into it. And together, the solvent and the solute together, they make a solution. Look at that diagram. The concentration that we use, the concentration, it will be a numerical value. That concentration is how many moles of the solute, how many moles of the dissolved thing have you put into a certain volume of solvent to make the solution. So it's per litre. We talk about how many moles of solute have you got per litre. Moles per litre. How many moles have you got of sugar per litre of sugar solution? How many moles of copper sulfate have you got per litre of copper sulfate solution? The industry standard is to talk about the units of moles per litre. Here, moles of solute per litre of solution. So the mathematical equation to use with solutions is this one here, N. N is number of moles. Number of moles of the solute that's dissolved. Number of moles of dissolved stuff in the solution. We're talking about the dissolved stuff. Number of moles of the dissolved stuff is volume in litres. Volume in litres, volume in litres, volume multiplied by the concentration, and the concentration must be in moles per litre. Moles per litre. And that is the third and final mathematical equation I want you to learn and be able to use. And remember where you can use it. You can only use it with solutions. Use it with solutions. You cannot use it with solids, liquids, gases. You cannot use it with volumes that are to do with gases. You must have a solution, and then you need volume and concentration. You need them both in order to work out how many moles you've got. And again, three unknowns, you should mathematically be able to rearrange them and work out, if you're given two of these, what the third one is. And you can use those daft little triangles if you want. So long as you get the answer correct, I'm not bothered. Now, these kind of ideas, the ideas of solutions, come up frequently in GCSE exams in titration calculations. The calculations where you've got an acid that's been reacted with an alkali. They tell you about the acid, they tell you about the alkali. They'll leave out something like the volume of acid needed, and you have to calculate it. That is a titration problem, and that turns into a moles problem when you have to do the calculation. you need to know to put a certain quantity, and we use burettes and pipettes. The pipette is this equipment, the burette is that equipment. One of them, the acid alkali, we get an exact amount here, it's the acid. They've pipetted it and they've spelt it wrong. They've pipetted it into a conical, and then they put some indicator in, and they've reacted it with an alkali from a burette. And these situations are what come up time and time again when we're dealing with solutions in GCSE moles problems. Right, the most important slide. You cannot do moles calculations without the three mathematical equations. There they are. That's the one I developed in my first Introduction to Moles video. Number of moles is mass over MR value, and the mass is measured in grams and the MR value. If you've got a gas volume, then you can use the middle one, volume in litres. You may have to convert to litres. You may need to divide by 1,000 to convert to litres if you've got centimetres cubed. But having got litres, you divide by 24, gives you the number of moles of it. And for a solution, number of moles, N, is a volume of that solution multiplied by concentration, and the units must be in litres for the volume and moles per litre for the concentration. So the red are the equations, the blue are the units. You must pay attention to units, and you must get this sorted. You must get it right. Otherwise, your answers will be wrong. And we don't want you doing wrong calculations. Right, okay. That deals with the fundamental core principles that underlie this topic. You need now to get on to doing calculations. So the nitty-gritty of the topic is the calculations. So what I'm about to do is arguably more important than like the hour or so that I've done before, the two videos, this video and the previous video. Now I've been whistling about an hour. Well, learn the method I'm about to teach you. This method will stand you in good stead, not just for GCSE calculations, but all of the A-level moles calculations. And moles is one of the harder things my students find at A-level. There's no need for it to be hard. You just follow this method. And this is the definitive moles method that you should get your mind around. Moles calculations method. First, can you see that in bold? You need to first learn and understand those three mathematical equations. Learn and understand those three. So learn and understand those three mathematical equations, and then you're ready to tackle a moles calculation. When you're ready, then read the question carefully. In every moles calculation, there will be one chemical. There will be one chemical that you can identify that you got enough data to work out number of moles of it. So if it's a pure chemical, we might have a mass. If you know the formula, you can calculate MR, and therefore you can work out moles of it. Or if you've got a volume of gas, if you've got a volume, divide by 24 litres to work out number of moles of it. Or if you've got a solution, the volume and concentration together, work out number of moles of it. What I'm saying to you is there will be one chemical. There will be one chemical, which I'm going to call it the first chemical. The first chemical, within that, you'll know enough about it to calculate the number of moles of it. So step one, calculate the number of moles of the first chemical using one of the three mathematical equations. So every calculation starts with which one of those do you need, and that depends on the context. So which one of those, and having got one of those, use it on the first chemical. And then you can work out number of moles of the first chemical. step 1 is done. There are only 3 steps to my method. Actually, it's not my method. There are only 3 steps to this moles method. I'm going to call it the definitive moles method, right? And whatever else you've learned about other methods, ditch it. Ditch it and do it like this. Step 1 gets you into the calculation. It gets you identifying one chemical. Having identified it, you are working out number of moles of it. It gets you into the problem. You don't waste time. You get into it, you get it started, and you're away rather than just scratching your head and wasting a lot of time and getting the answer wrong. So, step 2. Now, let me just cover that up while I talk to you about step 2. Step 2 is not a calculation. Step 2 is a write the equation and look at the number of moles of one chemical, compare it against the number of moles of another chemical. I know there's a lot of writing there, but the writing is to dispel you from thinking it's a long calculation. It's not. Step 2 is write the balance equation. Write the balance equation that has the chemicals that are reacting. So chemical 1, the first chemical in step 1, that one, the first chemical in step 1, that chemical will react with something else. And that's what you need, the balance equation in step 2 for. So step 2, then write a balanced equation for the reaction that occurs. So balance equation for the reaction that occurs. Sometimes that will be given to you in the question. If it's a common equation, then you may have to write it yourself. If it's not a common equation, they will give it to you. But you're going to use that balance equation to identify the second chemical. It's what the first chemical reacts with is the second chemical. And that's what you're writing this balance equation for. There will be a simple factor such as double, half or same. Now they're the words I use in my lessons. I say from your balance equation, one chemical, the first chemical, how many moles in the equation, how many moles does that react with of the second chemical? And somebody will put their hand up and say, sir, the same number. That's what I want. Same number. Or, sir, it's double the number of moles. Yeah. Or, sir, it's half. Now, most of the time, the answer is same, double, or half. Occasionally, it's 2/3, and they're harder moles problems, etc. But when you write the balance equation, it will become obvious to you what to do. So, use the balance equation, and the word here I want you to focus on is that word deduce. Deduce. It's not a calculation. You don't get your calculator out and do it. You deduce the number of moles of the second chemical that the first chemical is reacting with. So if you've got a number of moles of the first chemical, here is, the deduction is double it or half it or it's the same. It's that kind of thing. You do it by inspection. It's not a calculation. So step 2 is write the balanced equation. Step 3. Step 3 is use the 3 equations. Use one of those 3 again. So you used one of the 3 equations in step 1, and now in step 3 you use them again on the second chemical. Now the second chemical, you know more about it now. You know the ratio of how much is there from the balance equation. And knowing more about it now, you can use the 3 mathematical equations. One of them, and I know there are 3, but you only need one of them to answer the moles problem and get a final answer that you write down. So, step 3 is use whichever one's appropriate and answer the question. That's it. Now, I used to have a very good friend who worked with me, well, he's retired now, but he had a a system which he brought football into it. He says, step 1, work out number of moles of the first chemical. That's like the first half of a football match. And then step 2, this balanced equation writing, he said was like the interval between first half and second half. And that kind of like allows you to work out what's happening between the ratios of one chemical and another and get an answer for how many moles of the second chemical, number of moles that you'll have. It was this interval thing he talked about. And finally, the step 3 was second half, where you work out the answer, and at the end of it, full time, you worked out and got a solution to your problem. Now, you could think of it like that, but look, it's 3 steps. 3 steps, 3 simple steps. They're only going to be simple if you understand those 3 mathematical equations. And then applying these 3 steps allows you to get to grips with moles problems. So I'm going to work through 3 moles problems using my 3-step method. So, example 1, moles. When 8 grams of sodium burns. Now, the equation for sodium burning is complex, that's why I picked it. Calculate mass of sodium oxide that would be formed. So, step 1. Which chemical can you work out number of moles of? There. You can work out number of moles of sodium. Why? Well, you've got 8 grams of sodium, 8, and you've got a periodic table. On the periodic table, sodium, a mole of sodium atoms weighs 23 grams. Remember I said metals you can think of as atoms. So 8 grams of sodium, a mole of sodium is 23 grams. 8 divided by 23 is N. N is an acceptable abbreviation for number of moles. So here, number of moles, N, in brackets, sodium reads number of moles of sodium equals 8 over 23. That's step 1. Step 1, you worked out number of moles of one chemical, sodium. Any other calculations with other examples, you do likewise. You're going to use one of the 3 main equations. You can use one of them. You use one of them here. It's the masses one. And you work out number of moles. And I don't work out the answer. I leave the answer as 8 over 23. And then let's go on to the second balance equation step. The second step. Well, what's the sodium reacting with? Sodium is reacting with something in the air, and the stuff in the air is oxygen. You should know that burning is a reaction with oxygen. So it's reacting with oxygen. We need a balanced equation for how it reacts with oxygen. So that's the balanced equation. 4 sodiums with oxygen gas make sodium oxide. Can you see, if you didn't know the formula, the real oxygen gas is O2, then you'd be getting this wrong. Real oxygen gas is O2 and it makes sodium oxide, and you need to know the right formulae, and that's why moles is hard for people. They haven't got to grips with how to write correct formulae, which you need. They haven't got to grips with what real chemicals are. Oxygen is O2. It's never always a real chemical, always just a symbol for it. O2 is the real chemical. And sodium, to balance it up, you need 4 moles of sodium, because there's 4 moles of sodium there, 2 moles of oxygen, 2 moles of oxygen. And that balance equation is what, the half-time step 2, the balance equation thing is all about. We're not doing a calculation here. So now we want to link, what's the second chemical? Well, the second chemical is sodium oxide. How much sodium oxide do you get compared to the first chemical, sodium? Can you see? 4 moles of sodium, 2 moles of sodium oxide are made. From 4 moles of sodium, 2 moles of sodium oxide are made. So what's the second chemical? Number of moles of sodium oxide. That's the second chemical. And the answer is half. Half. That's at the half. Half the number of moles of sodium. The balanced equation gave you that. It told you it was half the number of moles of the first chemical. And if you know it's a half, then half the number of moles of sodium, well, that was the number of moles of sodium, 8 over 23. And now the number of moles of the sodium oxide is a half of that. Half of 8 divided by 23. And again, I don't do the calculations. I leave the calculation to my calculator at the end. So finally, we need to answer the question. It says calculate the mass. The mass of sodium oxide requires one of my three main equations, this one. Number of moles is mass over MR. And this is a real chemical, and now we're talking about sodium oxide. So mass, rearrange this, mass is number of moles times MR. So number of moles was this, half times 8 over 23, half of 8/23, multiplied by the MR value. Now you calculate the MR value. The MR value is, from the formula, 23, add 16, all that together. And you put that into your calculator, all of that. Put that into your calculator, get an answer of 10.8. Now, I want you to default in chemistry, the default to 3 significant figures, unless the exam question tells you otherwise. So if it says 1 decimal place, that would be that. If it says to the nearest gram, then it would be 11 grams. Read the question. But if the question says nothing, then 3 significant figures is the answer I want my boys to have. And let's look at that now. Step 1 was number of moles of sodium. Step 2 was number of moles of the second chemical, sodium oxide, was half. Step 3, you use this equation to answer the question. You get an answer. 3 steps and you've got it right. Now, practice that over and over again. Right, 1, fine. No, was that example? All right. Let's do example 2. Now, I've got an example 2. This is to do with gases. Gases. 25 grams of calcium carbonate reacts with excess hydrochloric acid. Calculate the volume of carbon dioxide gas that would be produced. So your brain may be a mess, but you focus on what you can work out number of moles of. 25 grams of calcium carbonate. That might be able to work out number of moles there. So 25 grams calcium carbonate, you know the formula of calcium carbonate. CaCO3. Number of moles of calcium carbonate is 25 grams. Remember, that's the masses. The masses mathematical equation, the first one. Mass over the MR value, 40 and 12 and 3/16, 48. 25 over 100 is 0.25 moles. So step 1, you worked out number of moles of calcium carbonate because it was talking about masses. You use the masses equation. But then step 2, we need a balanced equation. Balanced equation here. Carbonates react with acids. Carbonates react with acids, make salt, water and carbon dioxide. So you need to write the equation. And writing the equation, you need to know what your second chemical is. Well, your second chemical is carbon dioxide. And so that's that chemical there, carbon dioxide. And it's linked it to the first chemical. First chemical was calcium carbonate. Calcium carbonate, carbon dioxide. Those 2 chemicals, how many of each in terms of moles react? For every 1 mole of calcium carbonate, you've got 1 mole of carbon dioxide. The big number in front here is 1. The big number in front of carbon dioxide is 1. It's 1 to 1. And therefore, the number of moles of carbon dioxide is same. It's same. Same number of moles. And what was that number of moles? Well, it was 0.25. So the second chemical, carbon dioxide, same number of moles, 0.25. That's step 2. I know I might make a song and dance about it, but I want you to see just how logical this 3-step moles method is, and I want you to use it. Finally, answer the question. Well, the question wants a volume. Calculate the volume. If it wants a volume, you're going to have to use this volume, the second of my 3 mathematical equations. Volume over 24 divided by 24 is the number of moles you've got. So rearrange that for V. V is 24 times number of moles. So 24 times, well, the number of moles was 0.25 there. That's a quarter times 24. I didn't even need a calculator. 6 litres. That says 6 litres. If they wanted an answer in centimetres cubed, you'd multiply by 1,000 and you'd say 6,000 centimetres cubed and so on. This is a volumes question. Let me show you the 3 steps. Step 1. Number of moles of one chemical you can work out. Calcium carbonate. Step 2. Balance equation. The number of moles of the second chemical is the same. That second chemical is carbon dioxide. Step 3. Volume of carbon dioxide. Use the volume in gases mathematical equation to work out the answer. There. Finally, let's deal with solutions. What volume of such a concentration, see, concentrations are in moles per litre. Sodium hydroxide will just neutralise 20 centimetre cubes of 1 mole per litre nitric acid. Now, this is like in the context of that titration type experiment I was talking to you about. But the method just works, and it's just the same. So, which one can you work out number of moles of? We want a volume and a concentration. Well, sodium hydroxide, we've only got a concentration. Look here, volume and concentration, nitric acid. So that's our first chemical, nitric acid. Number of moles of the first chemical, nitric acid. Here we go. Nitric acid. Number of moles of it is volume in litres. So it's 20 divided by 1,000. A lot of my students forget that. Don't forget that. Convert it to litres. 20 over 1,000. 20 over 1,000 is the conversion into litres and gives you an answer multiplied by the concentration of 1.00. So number of moles of nitric acid is that many moles. Easy, because that's all you could do. The only number of moles you could work out was nitric acid, because you had a volume and a concentration. Next, balance equation. Sodium hydroxide, nitric acid reacts to make salt and water. So what about the second chemical, which is sodium hydroxide? Sodium hydroxide, the number of moles of it is the same as the nitric acid moles. And the nitric acid moles, 0.02. So that's a 0.02. You see how easy it is? And finally, you've got to answer the question. Well, answer the question, we're going to use the solutions, number of moles mathematical equation again, and rearrange it because it wants what volume. Volume is number of moles over concentration. The concentration of sodium hydroxide is 0.5 molar. And the number of moles was here, 0.02. And you divide the two, you get an answer of 0.04 litres, which, if you multiply by 1,000, is 40 centimetres cubed. What volume of sodium hydroxide will neutralise 20 of that? Well, 40 of it will neutralise. So 40 of sodium hydroxide will be needed in that titration to make your indicator change colour. Anyway, look, my last slide is probably the most important slide of all. And I might say nothing over it. Actually, that's not my last. Yeah. Let me just go over the 3 steps. Step 1. Number of moles of nitric acid was the first chemical. Step 2, number of moles of sodium hydroxide. We got by deducing it was the same as nitric acid. Step 3, we work it out as an answer. Right, now my last slide, probably the most important of them all. As a mathematical topic, I cannot stress enough that you must do drill exercises. You must do this over and over and over again. Lots and lots of different situations that you do my three-step method. My three-step method will serve you well, and you'll need it right the way through A-level anyway. If you learn some other method and there are other good methods, but if you learn them, then you're going to have to learn this method at A-level again. So just learn this from the word go. Ditch your other methods. You can do everything with this. That's the most important thing. Use your calculator. Do lots and lots of moles calculations. It surprises me year in, year out why so many boys and students cannot use their blinking calculators. So learn to use your calculator. Learn to do calculations. And good luck. Moles problems are not as difficult as they seem once A, you understand the underlying principles, as in my first video, and B, you try and use the three-step method that I've been whispering on about this video. Alright guys, see you next time.